All right, thank you so much. Just a fair warning, I probably tried to fit too much into an 18-minute talk, so I'm gonna try to move at a deliberate pace to make sure I get through everything and just jump right in. My name is Adam Shield. I work at Antares, better known as AutoTune. I was on the team that built AutoTune 2026, which just came out a couple weeks ago. We're really excited about that, and I'd love to talk to any of you about that at any time during the conference. But the inspiration for this talk actually came from a side project I was working on called Qiti, which I'll just quickly note is free and open source. Feel free to try it out and see if it helps you in your workflows at all. But basically the idea behind it was I was looking to find ways to enhance or add additional tooling and features to our C++ testing framework. So by testing framework, I'm referring to, like G-test, catch2, juice unit tests, basically however you're directly testing your C++ code like in CI. I was looking for ways to add additional tooling to that for like detecting memory leaks, data races, things that there's already wonderful tools to do those things, and this doesn't compete with those tools, but the idea was to try to bring it into the testing framework so that it could be easily run in CI and have that sort of workflow. And then I'll just note that those things all required like instrumenting the code, so that's sort of the theme of the talk. So the layout of the talk is sort of as follows. We'll quickly note, I'll quickly explain what I mean by instrument. It's instrumentation. We're going to talk about 3 tools that are in Qiti that I added to that library, which can be built using these instrumentation techniques. For each of these tools, like I said, we'll talk at a high level about how you could build them, like what are some solutions that I use that you could use as well. I'm gonna skip the review slides just to make sure I stay on time, and then I'll just show you an example of what the API looks like in Qiti in case that's useful to you. Okay, so stepping right in, what is instrumentation? In the context of this talk, I define it as the injection of new behavior into pre-existing code. And I'll add usually for the observation of runtime behavior. So there are other reasons you might want to instrument your code, but for the examples here today, it's more about the observation of the runtime behavior. And I'll also note that I'm visualizing these as something you can flip on and off. You might hide these features behind some kind of custom flag that you set that you might turn it on whenever you're compiling your tests and then add these features. So the first tool I sort of wanted to talk about that you can do is a heap allocation tracker. So let me just show you an example of why you might want to build that. Let's say you had a test that looked something like this, and what you wanted to do was you wanted to assert that for a certain function, you didn't heap allocate. So we know that like heap allocation on the audio thread is a no-no. So let's for the test, we could say, okay, let's get how many heap allocations I've done, run the code that should not heap allocate. The constructor probably shouldn't be there, that's a mistake. But, and then test again how many heap allocations we've had, and then the test could be that the before and after values are the same. So this is actually pretty easy to implement. You might have seen this before, but in C++, you can override new and delete itself. So this is literally, overriding, the actual new and delete keywords. And then what's on the screen right now is sort of the default implementation for new and delete. So this would basically mimic regular behavior, but then you can instrument it. You can inject your own logic and behavior into it. So to accomplish the test that we were imagining in the previous slide, you could just have a variable which keeps track of how much has been allocated, and then in operator new, you can add to it and then keep track that way, and then have some kind of getter or something. But let's say you wanted something more sophisticated than that. Let's say you wanted to actually detect memory leaks, so that not only do you need to know how much has been allocated, but you also need to know how much has been freed. You need to know both sides of that equation. So again, you might want to know how much is currently allocated that has not yet been freed, run your function that you want to assert does not leak, Again, check how much is currently allocated, assert that the before and after are the same value. Here's how you could do that. First of all, I just kind of want to draw attention to the signature. Operator new does tell you the size of the type that you're allocating, but operator delete does not. It'd be a little tricky to keep track of exactly how much you've deleted. But what you could do, and don't be overwhelmed by the amount of code on the screen, I'll just zero in on what actually matters. What you could do is use some kind of dictionary-like object, like an unordered map, so that when you're in operator new, you can associate with the pointer that you're allocating to how much you've allocated to it. And so you could just you could just set how much you've allocated to it. You could also instead of storing just a number, you could store like a data structure that stores a bunch of information. But the point is now you can detect how much you've allocated and deleted, and again have some sort of getter for that for your test. And then this other code here, I just wanted to just briefly mention, this is like basically like an infinite recursion check, because as soon as you try to modify the unordered map, then you'll be heap allocating again, and you'll be back in operator new, and then that will repeat forever unless you just do something to stop it. So that's going to happen several times in this talk, so you have to have some kind of way to prevent these infinite loops. Another quick pro tip is that you could make these values thread local, which for those who don't know is a useful keyword. It makes it so those variables have a copy on every thread. So now what's happening in operator new and delete basically will be independent on each thread. So like let's say you're testing something, you don't want something that's happening on another thread, maybe that allocates, you don't want that to throw off the values of your test. So this is just one way you could handle that. Skip that slide. This is what it looks like using the Qiti API. Basically, all you'd have to do is just initialize Qiti. You run get function data on the function you care about, like let's say process block. And then you run that code, and then that function data is a data structure which stores all kinds of information that's updated in real time as you're running the code. And then from that, you can say, okay, get the last function call. From that, how many times did that function call heap allocate? You could assert that that's 0. So that's what that looks like using that library. So moving on, the second tool I just kind of wanted to talk about was a function profiler. So this is where it gets into the territory where the library becomes Clang only, because I'm using a Clang flag to do this. So there's a flag that Clang gives you called instrument functions. Basically, when you compile your code with this flag enabled, it adds these hooks to every function. So every function that's called, that's compiled this way, at the beginning of the function, it'll call this enter function. At the end, it'll call this exit function. So you can now like hook into every function and track like how long were you in that function or all kinds of other information. This is very handy. One thing you should know about if you're implementing this though is that they give you this attribute you can add to any function to make sure that that function isn't hooked into. So this is a way of like excluding a function, and you actually do want to add it to the hooks themselves, else the hooks will hook into themselves. Again, an infinite loop, something to be aware of. And then you might want to actually put the logic that you're instrumenting your code with. You might want to put that in some kind of infinite recursion loop as well. Else, again, you'll just keep going right back into the hooks. So again, for this tool, you could use some type of dictionary-like object, an unordered map. For each function pointer, you could keep track of how many times it was called, but you could keep track of all kinds of things. Again, you could have some sort of data structure that stores, how long were you in the function? Like, what is the average time you're in that function? Minimum, maximum. What threads are calling this function? Was there heap allocation? You could even check the stack trace inside the hooks and then find out what function called this function if that's important to you. There's just a lot you can do with these hooks. And then here's what function profiling looks like if you're using the Qiti API. Again, you just initialize Qiti. You say, I want to get the function data about, let's call process audio. And then this example, I call it twice, and I can assert that it was called twice. Obviously, your test could be more sophisticated than that. But normally, you would use something like gmock for this, but that can be very unwieldy. It can require you to actually change your code to make a bunch of functions virtual that you didn't want to be virtual. I think this is a lot more intuitive and easy to use, personally. So that's what that is. And then the final tool I just wanted to mention, and this is what inspired the whole investigation in building this library, is a data race detector. So the solution for this is a little bit more complicated, but basically, let's imagine the test was, here's an example of an obvious data race. We have two threads, both modifying value at the same time. Undefined behavior. If this happens in our code, it would be great if we could just detect it as soon as we write something like this. What I wanted and visualized was I wanted to have a snippet of code and be able to say, does this contain a data race? So I had to sort of work backwards from there. Basically, what you can do, and this is another Clang only feature, Clang gives you flags you can set to turn on thread sanitizer. So the main flag for this is sanitize thread, but for this all to work, you'll need all three of these flags. But basically, and then also you can set additional options with this optional override function. So what I used this for was to set where the log was written to, the thread sanitizer log. And we'll get to why that is in a second. So here's what the thread sanitizer log looks like with the code that I showed earlier with the obvious data race. Basically, it's pretty straightforward. It says we found a data race. It was it was for the variable called value, and it was with these two threads on these lines of code. So if there was some way to examine the log, parse it out and say, okay, did the code that ran, did that have a data race? That would be very, very useful. That could be a way to do it. The problem though is that the application needs to conclude. Like you need to run basically you have to run the full tests, and then when the application is finished, then the log is created. So I was trying to figure out a way to how can I run some code in a sandboxed way such that if there's a data race, it creates that log, and then we can check the log for a data race. And the semi-elegant solution I came up with was to fork the current process. So for those who don't know, on Unix type systems like Mac OS, Linux, you can literally just call fork, which creates a copy of the current process, and then runs them basically as a child and parent. And so what you could do, and this is an oversimplification, of course, but what you could do is say, all right, let's just pass in like a lambda containing whatever snippet or function or whatever that we want to test, and then have the child process run that and exit. And then when it exits, it'll, if thread sanitizer caught anything bad, it will write that log. We know where we wrote that log. The parent can just wait for that to happen, and then look at that log and find was there a data race, and then you can pass or fail your test based on that. And so this is the last slide. This is what that looks like if you were to use Qiti to do this. You do have to turn this feature on because then I set those thread sanitizer flags for you. But basically, you initialize Qiti, you say create data race detector. You tell that detector to run the code you're interested in. It handles all of the forking and the parsing of the log for you, and then you can just assert that your code does not have a data race. I hope some of that info dump was useful to any of you. Would love to talk more about this during the conference, but that is my time. Thank you so much.